Hi, I'm Brian Faith, CEO of QuickLogic, and I'm excited to be here at GTC today to talk about accelerating innovation at the edge with our technology. The agenda I'm going to cover today, firstly, is going to talk about the design considerations and challenges for AI at the edge. We'll talk about some use cases for solutions around embedded FPGA. We'll be focusing on 22FDX, a great process from GlobalFoundries. And then at the end, we'll wrap it up with a really exciting project that we're embarking on today with the Open Hardware Group, GlobalFoundries, and QuickLogic. But again, first, let's start talking about some of the design considerations and challenges around AI at the edge. So firstly, what is the edge or what is the endpoint? These are devices that have lots of different sensors. We're talking about sound and vibration and motion, image sensing. More of these sensors are getting deployed very far from the core of the network, out where typically there's a power concern or it's battery powered. Size is a concern. There might be thermal constraints. Example applications could be falling into the categories of consumer or industrial. On the consumer side, we typically see things like hearables and wearables and smartphones, other consumer devices you might have around your house falling under that IoT umbrella. On the industrial side, there's a lot of stuff going on now with predictive maintenance and in IoT and industrial settings. And in almost every case, everything starts with a sensor, and you want to take data from that sensor at really low power and convert data into meaningful, actionable information. And that's the trend that we see today. Is there's sort of explosion devices that fall into those categories. Now, there's a lot of design challenges associated with building products that meet these needs. And if we look at the core silicon that goes into these edge or endpoints, you have all of these opposing forces coming to play. So one is time to market. Obviously, as markets move quickly, you want to get into the market and lead the market because people that are in the market first typically get most of the profits. But then the counterbalance to that is that you want to make sure your silicon is correct because anybody that knows how to design silicon knows it's actually a very expensive proposition. So you have fragmented markets, and how do you deal with features for these different fragmented markets? You have regional requirements in some cases. We think about different standards evolving based on the geography and how they might change over time. And then, of course, you have this underlying concern, especially as you get further and further from the core of the network around battery life. And how do you manage all of these opposing forces when you're architecting your next SoC for these markets? And so as we look at this, and we've been doing this for nearly 3 decades, is using programmable logic in more complex devices to handle all of these different opposing forces. The traditional way to look at this, if you're designing an SoC, is you could say, well, I'm just going to do everything in software. I'm going to put a lot of processors, maybe 10, 12 different little processors in there, and I'm going to distribute my software across all those processors, and that's my solution. And that has high level of flexibility, but it's not very optimized. On the other end of the spectrum, you can do everything in hard gates or an ASIC. And that's going to optimize for space and power and cost, but it's incredibly inflexible. And so we think about, fragmented markets and things changing. How do you handle change if you're going to fix all the gates? It's difficult to do that. So we actually see that, especially if you look into the ASIC market, if you're going to do 100 million units, ASIC is probably a good choice. If you're doing a smartphone chip, great choice, because you know that you're going to be selling enough volume to justify the high NRE for all that. But markets change, customers change, especially in the consumer market. Consumers are fickle and things change. How do you adapt to that? With AI coming out, there's so much innovation happening in AI and the algorithms that people are using for that. How do you anticipate what those changes are going to be? How can you have a platform that can be flexible as those innovations occur and actually enable that? That's where we actually think embedded FPGA is a perfect intellectual property to add to these SoCs because yes, you can do everything in software, but inevitably you start running out of MIPS, you start running out of memory, algorithms need to change. How do you handle that, especially if you want to hardware accelerate something? Embedded FPGA, when it's tightly coupled with processors and the peripherals on the same platform, gives the platform that extra level of programmability that you wouldn't otherwise get so that you can handle these nuances of these markets. So when we look at embedded FPGA, we think about a few different use cases, and they're shown here. One is the efficient calculation use case. That's where you can do something in software, But if you want to go massively parallel to do things in a much more efficient way, embedded FPGA is a great way to do that. The second, and the one in the middle there, is the precise timing. Doing things in software is possible, of course, but if you need absolute timing, if you need very precise timing on the I/O, FPGAs are a very predictable way of doing that. And then the last one on the right, we talk about independent or autonomous operations. This is where you can offload a lot of control, especially system level control, to programmable logic, offload it from the processor that can often get interrupted by other tasks. So if you start double clicking on these, one example that's fairly common actually is the hardware offload or accelerated DSP. This is where you might be doing something for a hearable device, and you're doing all these different audio algorithms. How do you take some of those algorithms and move them off to the hardware so you can free up MIPS and memory and do things in a more parallel and lower power way? Again, FPGA, embedded FPGA specifically, is very good for that, especially when you tightly couple that with the embedded processor. Another use case is I/O expansion. Oftentimes, if you're doing an SoC and you decide to take it to a new market, you might have different I/O requirements in a different market. And instead of doing a multi-million-dollar, multi-quarter design spin to go handle a few different I/O, using embedded FPGA to repurpose that logic for those new I/O standards is a very common use case, and you can accommodate that with embedded FPGA. A third example is called real-time I/O control. This is what I was talking about a little bit earlier, where you want to have sort of microsecond level control or precision of waveforms, interaction with different sensors or motor control or actuators. Programmable logic will give you that precision, and it will not get interrupted from the processor doing other tasks. So you really have a very predictable system, which is important, especially when we start looking into some of the industrial control applications. And then this last one is probably the one that's getting the most press these days. This is around all this AI innovation that's going on. Yes, you can run AI neural networks and software on processors, but if you want to go more parallel, embedded FPGA is a great way to do that, especially for some of the use cases I'll be talking about in a second. And I think we see today, working with our AI software company called SensiML, or integrating things from TensorFlow Lite for microcontrollers that Google is putting out. Embedded FPGA is just a very good way of implementing those things for lower power and higher performance. And that kind of gets us to this case study on 22FDX that was done as a collaboration between ETH and Zurich and QuickLogic. So specifically, we started looking at this use case around visual wake words. And a visual wake word is basically taking an image from a camera, a video, and understanding if there's somebody that stepped in front of the camera so that you can say that there's a person or not. And you could understand, or I think envision, how this might roll out in a consumer product from a security point of view. You know, disable everything until you see a person come in front, and then you can activate things. Security cameras in the home are another example. Anyway, this is called visual wake word. And we've actually taken that visual wake word from TensorFlow Lite and actually implemented this on this test chip that was created by ETH and Zurich. Just briefly on this chip, it's called Arnold, and you can see that on the die there. It's a combination of a 32-bit RISC-V core with a tightly coupled embedded FPGA from QuickLogic, built on 22FDX, got really good performance on the processor. It's also got really good offload capability on the embedded FPGA. And you'll notice the FPGA in the middle there has interfaces to I/O, to DMA, to their low latency interface, to the processor, and then also to these math blocks on the north side of the FPGA there. All of these have a really good, well-defined data flow so that you can offload and do all the different use cases that I was talking about earlier. If you're interested in the research part of this, you can go to these links later after the presentation. So the bottom line, in implementing the TensorFlow Lite neural networks as a hybrid architecture, some of the software running on the processor, some of the software implemented on the embedded FPGA, we're able to see a substantial increase in performance or a substantial decrease in power. And the beauty of having this on one chip with embedded FPGA is it gives the power to the user. You can dial in what you want. Do you want more performance at the same power, or do you really want to go aggressive on battery life and drop that power for the same level of performance? And you can see the frames per second and the power here, very low, and this enables it to be used in an always-on IoT use case. Again, enabled by both the 22FDX process from GlobalFoundries, the architecture as it was defined by ETH and the embedded FPGA from QuickLogic. So now let's get a little bit more into what is this embedded FPGA from QuickLogic. QuickLogic, firstly, is a fabless semiconductor company. We're based in Silicon Valley. We have 3 primary product lines. We have an embedded FPGA intellectual property line of business. We use some of those IPs in our SoC line of business. And about a year and a half ago, we acquired an AI software platform company that sits on top. Really gives us a full stack of technology that we can license or interact with different partners to bring very intelligent solutions to the edge and to the endpoint. And we absolutely focus on power sensitive or low power systems. So our embedded FPGA, without getting into the details, is it's an array of programmable logic. We've been in this business for 30 years. We know how to do FPGA technology and how to integrate that into hybrid architectures. We have an ability to configure these arrays for different densities, different geometries. And again, we're very focused on power. We're very aware of what it takes to do low power system design. And so we have a lot of different knobs and handles that you can turn or flick the switch for power optimizations in the embedded FPGA core. Very routable. And of course, we have all the accompanying configuration logic that you would need in order to integrate that into your own SoC. So a really exciting initiative for us we launched a couple months ago is called QORC, the QuickLogic Open Reconfigurable Computing Initiative. That was done as a collaboration with Google and Antmicro, 2 big players that are very huge proponents of open source. And so this whole initiative was taking our proprietary programmable logic technology and the FPGA tooling to use it and move a lot of that information and technology into the open source domain. So this really gives sort of power to the designer to take our tools and customize, makes it a lot more efficient for integrating into the end user's workflow. And again, fully open source, and along with the software, we're doing things like these open source development kits that we're getting out through Crowd Supply and QuickLogic and our distributors to really promote this notion that, yes, it can be easy to change hardware for the software engineer with all these great open source tools. The big FPGA tooling initiative here that was launched for the first time with QuickLogic was SymbiFlow support. It's full HDL to bit stream. You can take Verilog, go all the way through the flow, program it into the gates, all open source tooling, no proprietary tools there. So really this is all around enabling more compute at the edge and the endpoint with open source tools within your power budget. And it's really exciting to be a part of that launch. Now, where that sort of couples with what we've been talking about today at this GTC event is a collaboration between Open Hardware Group, GlobalFoundries, and QuickLogic. And we're really excited to join a lot of these open source initiatives. We joined CHIPS Alliance, we've joined Open Hardware Group. The big thing with the Open Hardware Group is that this is a non-for-profit entity out of Canada. A lot of different players in the semiconductor space have joined this entity, the goal of which being that we have proprietary cores that are now moving into open source, like RISC-V. How do we take those cores and make them verified so that people feel comfortable and low risk enough to take those cores and integrate into their own SoC? And that's one of the charters of the Open Hardware Group. And a couple weeks ago, we announced through the Open Hardware Group this initiative to bring an MCU SoC to tape out in Q1 of 2021, largely based on everything I just talked about with the Arnold SoC from ETH and Zurich, but again, moving this core into the more verified version of this coming out of the Open Hardware Group, embedded FPGA from QuickLogic, all the peripherals associated with what you would want out of a world-class low-power MCU. And you can see the specs here on the right that we're shooting for. And again, this will be built in 22FDX at GlobalFoundries. So we're thrilled to be a part of that. And want to see if other people would want to join this collaboration to bring this to market, and so everybody can really benefit from having a proven platform with this out there. So that's my presentation today. I'm really thrilled to be here at GTC to share with you all the things that QuickLogic is doing to accelerate innovation at the edge. And if you are interested, if you have other questions, feel free to reach out to me on email, ping us on Twitter, or just give us a call. Thank you very much. Bye-bye.